Okay, so today we're doing proof by induction where we're involving division. So we still have the same learning intention. We're going to gain a better knowledge of the process of the performing proof by inductions. We're still having to apply correctly the 4 steps of proof by induction. Okay, so the first example, we want to prove that 9n plus 7 is divisible by 3. So our first step, is to prove the base case. Alright, so we're going to let n equals 1. Okay, so that means that we get 9 to the power of 1 plus 7. Well, that's 9 plus 7. That equals 16. Sorry, not divisible by 3, we want divisible by 8. Sorry, I wrote the question down. This should be divisible by 8. Yeah. So this is, which is divisible by 8. 16 is divisible by 8. What it is, it's 8 lots of 2. Okay. So that's the first step. The second step is the assumption for n equals k. So we're going to assume statement is true. So statement is true for n equals k. Assume statement is true for n equals k. And what that means is we get 9k plus 7 is divisible by 8. That's what we're trying to say. And the way we can write that actually is we can write it as 9k plus 7 is 8 lots of some number. Yeah, because if you want something to be divisible by 8, well, it has to be a multiple of 8. That's what it means. And what I'm going to do is I'm just going to rewrite this as 9k is worth 8p minus 7, making 9k the subject. Okay. Now step 3 is that we want to require to prove that's going to be true for n equals k plus 1. Alright, so we're required to prove statement is true for n equals k plus 1. And what does that mean? That means that 9 to the power of k plus 1 plus 7 is divisible by 8. Yep. So that means that 9 to the power of k plus 1 plus 7 is worth 8 lots of another integer, q. Yep. So where q is an integer. Okay, so working with the left-hand side. I can write this 9 to the power of k plus 1 as 9 lots of 9k plus 7 using indices laws. Okay. Now, using my assumption that n equals k, I can substitute this 9k for 8p minus 7. So now what I'm going to do is I'm basically just going to expand this out. And what I've got 72p minus 56. If I take out a common factor of 8, I get 9p minus 7. So I get 8 something. Yeah, and then, so you can imagine that q is worth this. Okay, which equals the right hand side as p and q are integers. All right. So my fourth step is the conclusion. Okay. So since the statement is true, for n equals 1, and if true for n equals k, it is also true for n equals k plus 1. So 9n plus 7 is divisible by 8 for all integers n is greater than or equal to 1. Okay, example 2. We want to prove that 8n minus 5n is divisible by 3. So once again, step 1 is the base case. So we're going to let n equals 1, so we get 8 to the power of 1 minus 5 to the power of 1 is 3, which is divisible by 3. So statement is true for n equals 1. Step 2 is the assumption. So assume statement is true for n equals k, so that 8k minus 5k is divisible by 3. So we get 8k minus 5k is worth 3 lots of a number. Okay. Step 3 is required to prove n equals k plus 1. So remember that step 1 and step 2 is what we call the inductive step. So we're required to prove 8k plus 1 minus 5k plus 1 equals 3q, is divisible by 3, so that we get 8k plus 1 minus 5k plus 1 equals 3q, where q is an integer. Okay. Now, the left-hand side is 8k plus 1 minus 5k plus 1. I'm going to rewrite this to have 8k as a subject. So that we get 8 lots of 8k minus 5k plus 1. Using my assumption, I get 8 lots of, subbing that in, 3p plus 5k minus 5k plus 1. So I get 8 times 3 is 24p plus 5k multiplied by 8 minus 5k multiplied by 5. Yep, that's that term multiplied by that, and that's 5k multiplied by that 5 plus 1. If I just collect my 5k's out the front, 8 take away, I get 8 minus 5, and that becomes 3. Just swap them over. Okay, now I'm going to take out a common factor of 3 from both sides. So I get 3 lots of 8p plus 5k. Yeah, which is divisible by 3 as p and k are integers. Yeah, so statement is true for n equals k plus 1. So step 4 is conclusion. So since the statement is true for n equals 1, and if true for n equal k, so it is true for n equals k plus 1, an minus 5n is divisible by 3 for all integers where n is greater than or equal to 1. Okay, the third example. We want to prove that 3n plus 7n is divisible by 10 for all odd values of n. Alright, so step 1, the base case. I'm going to still let n equals 1, because the first value is 1, and 1 is an odd value. Yeah, so in this situation, n will be equal to 1. Okay, we get 3 to the power of 1 plus 7 to the power of 1, which is 10, and that is divisible by 10. Yeah. Step 2, the assumption. Okay, we're going to assume that statement assume that statement is true for n equals k. So that means that we get 3k plus 7k is divisible by 10 when k is an odd number. Yeah. So we get 3k plus 7k equals 10 lots of a number, where p is an integer and k is an odd integer. Okay, and what I'm going to do is I'm going to rewrite this with 7k being the main subject. Okay. Alright, step 3. prove the n equals k plus 1 situation. So we're actually required to prove that n equals k plus 2 is true. And the reason why I said n equals k plus true is if we're looking at only the odd values. If k is odd, the next odd value would be 2 numbers after that. Yeah, so really in this situation we're going to require to prove that n equals k plus 2 is true. So that 3k plus 2 plus 7k plus 2 is divisible by 10. Which means we get 3k plus 2 plus 7k plus 2 equals 10q, where q is an integer. Okay. So we actually get 3k plus 2 plus 7 squared, 7 multiplied by 7. So we're just looking at the left-hand side. So using our assumption, the left-hand side is worth 3k plus 2 plus 7 squared, and 7k was 10p minus 3 to the power of q, 3 to the power of x. All right. Well, that is I'll leave that as 7q times 10p minus, okay, if I'm going to collect the 3 to the power of x, 3 to the power of k, we get 3 squared minus 7 squared. So that's 9 minus 49, which is basically minus 40. And this still becomes 49. So that's 490. So what we can now take out is a factor of 10. So if I took out a factor of 10, I get 7 squared p minus 4 lots of 3 to the power of k. Yeah, and that is divisible by 10 as p and k are integers. Alright, so step 4 is your conclusion. So since the statement is true, for n equals 1, and if true for n equals k, it is true for n equals k plus 2, 3n plus 7n is divisible by 10 for all odd values of n when n is greater than or equal to 1. Okay, and that's it for this proof. Okay, thank you very much.